Imagine a smart building where dozens of ESP-32 sensors report data to a central dashboard in real time. HTTP requests for every update would quickly flood the network, drain power, and complicate coding. MQTT, a lightweight publish-subscribe protocol, solves this by letting devices send data to a broker, which then distributes it only to interested clients. In this lesson, we'll configure an ESP-32 as an MQTT client using ESP-IDF, enabling it to publish messages, subscribe to topics, and handle real-time events. By the end, you'll be able to integrate your ESP-32 into efficient, reactive IoT networks, understand broker interactions, and apply best practices for reliable message delivery, laying the foundation for scalable, multi-device systems. Think of MQTT as a newspaper system. The broker is the post office, topics are different newspaper sections, and your ESP-32 is both a reporter and subscriber. When a device publishes a message to a topic, the broker distributes it to subscribers automatically. This reduces unnecessary traffic, unlike HTTP where every device must poll for updates. In ESP-IDF, MQTT uses an event-driven model, triggering callbacks for connection, message arrival, and disconnection. Topics are hierarchical strings, and payloads can carry sensor data or JSON commands. Quality of service, QoS, levels define delivery guarantees, letting you balance efficiency and reliability. Reflect on how this pattern simplifies large-scale IoT deployments and prevents your devices from being overwhelmed by network chatter. To start, we initialize the MQTT client with broker URI and optional credentials. In ESP-IDF, the ESP_MQTT_client_config_T structure stores these parameters, and ESP_MQTT_client_init prepares the client. Event handling is crucial. MQTT_event_connected allows subscription setup, while MQTT_event_data triggers whenever a new message arrives. In practice, I always log each event to monitor connectivity and debug payload issues. Publishing messages involves specifying the topic, payload, QoS, and retention flags. Think of it like sending letters. You address the topic, write the content, and decide whether to guarantee delivery or just send and move on. Proper event handling ensures your ESP-32 can recover from network glitches without manual intervention. Here's a minimal ESP-IDF example demonstrating connection, subscription, and publishing. The code begins by including free RTOS, logging, and MQTT headers. The MQTT_event_handler handles connection, disconnection, and incoming messages. In app_main, we configure the broker URI, initialize the client, register events, and start it. A loop publishes a temperature value every 5 seconds. Line-by-line comments clarify function purposes, from subscribing to a topic to publishing a payload. Visualize this as your ESP-32 continuously reporting to a broker while listening for commands, enabling two-way communication in a real-world IoT network. Because MQTT follows a publish-subscribe model, any client subscribed to ESP-32 temperature will instantly receive these updates. This structure makes IoT systems scalable, efficient, and reliable, especially when multiple devices interact in real time. From experience, most MQTT client issues arise from misconfigured broker URIs, missing event registration, or lack of reconnection logic. Always verify that the ESP-32 is on the same network as the broker, and consider network latency when choosing QoS. Log every event to trace issues quickly. In production, I implement a watchdog that detects disconnection and triggers reconnection attempts. For payloads, using JSON makes your messages extensible and readable. Reflect on how robust event handling and structured payloads prevent subtle bugs and make scaling to tens or hundreds of devices seamless. Once comfortable with MQTT basics, extend your client into practical projects. For example, subscribe to ESP-32 LED and toggle the onboard LED based on received commands, simulating a remote actuator. Create a temperature dashboard that aggregates multiple ESP-32 clients publishing sensor data. Experiment with QoS 0 versus QoS 1 in lossy networks to observe message reliability. These mini projects teach you real-world design considerations like traffic management, latency handling, and device coordination, all while reinforcing your MQTT client skills. Ask yourself, how would I coordinate multiple ESP32 devices without overload in the broker? By completing this lesson, you've learned to configure the ESP32 as an MQTT client, understand publish-subscribe architecture, handle events effectively, and publish or subscribe to topics reliably. These skills are essential for building scalable IoT networks, controlling devices remotely, and integrating real-time telemetry. You can now confidently design ESP32 applications that communicate efficiently, handle network fluctuations, and support multi-device environments, preparing you for advanced automation projects.